Welcome to this Intro to Capital Modelling with Python lecture. I'm Dan Gelderd. This is the second in a series I'm doing on dependencies modelling. And this one is about the things you can control and things that you can't control so well, and why this matters to you when you're choosing a dependency structure. So we're going to set up a simple scenario. We're going to build an insurance risk dependency model, and we're selecting between two alternative approaches. In both cases, we're interested in correlating reserve risk and underwriting risk together, and we're interested in correlating classes together. And the two methods that we're going to consider really just vary based on what order we do these things in. So method one is going to correlate insurance risk between the classes, whereas method two is going to correlate underwriting risk and reserve risk separately between the classes. And just to clarify what I mean by some of these terms, reserve risk, I'm meaning the risk on earned exposures. Underwriting risk is risk on unearned or future exposure, and by insurance risk I'm simply meaning the sum of these two. And we're going to look at these. They're both intuitive and reasonable approaches that you will see in real life capital models, but we're going to have a look at their practical implications, in particular their stability, as we change the seed and do random seed testing, and importantly as we change the underlying exposure volumes in the model and we see what impact this has on the results. So let's just have a look at those two methods in a bit more detail so we understand what we're doing. The insurance risk based correlation approach, this is the method one. So we're first going to correlate the underwriting risk and the reserve risk together within each class. We're going to then aggregate them to give a total insurance risk value per class. And then as a second step, we're going to correlate the insurance risk totals together across the classes. And that's going to give us our total insurance risk figure. So you can think about this method as being the kind of risk periods get correlated together first, and then the classes. When we look at the second method, we do it kind of the other way around. So first we're doing the class-to-class correlations within underwriting risk to give us a total underwriting risk figure. And we're doing the class-to-class correlations just attaching to reserve risk to give us a total reserve risk figure. And then as a second step, we're doing total underwriting risk to total reserve risk. So this is like class level correlation first and then risk period correlation. So it's the opposite way around. Now, what do I mean by controllables? Now, this isn't a technical term. This is just a kind of very informal idea, but I think it's a useful mental framework when you're thinking about why one of these structures might work better for you than the other. So if we look at the method one, what we're calling the insurance risk correlation approach, let's have a look at the things we can control easily. And generally this is going to be the nodes, the explicit nodes that you see on this hierarchy diagram. So if I want to change class 1's insurance risk total, it's clear that I can change this just by moving the parameters for the correlation between underwriting risk and reserve risk for just that one class. I wouldn't affect any other classes. I don't have to change the underlying underwriting risk for that class. I haven't got to change the underlying reserve risk for that class. So none of the other sort of important metrics in the model need to move. I can just dial up and down that one correlation strength and I'll affect class 1's insurance risk. So I can clearly affect class 1's insurance risk. And so I would say that that insurance risk figure at the class level is a controllable. Now we've got the total included here as well. It's inevitable that we're going to affect the total result as we move any of these things around. So I'm kind of not really counting that one too much, but really the rest of the diagram is left unaffected as we change this class 1 insurance risk figure. And as you see, the total insurance risk is itself a controllable because I can change the insurance risk correlation between classes. I won't change the class 1 total insurance risk. I won't change any of its underlying underwriting risk or reserve risk, but I can just dial up and down the correlation strength between the classes, and that's going to affect the insurance risk total and nothing else. So I would say the insurance risk total here is another controllable. If we go across to the second method, the one where we do class correlations first and then the underwriting and reserve risk correlation second, I can control total underwriting risk by changing the correlations between the classes for underwriting risk. And that's going to affect that figure. It's not going to touch any of the reserve risk figures. So again, so at this point, I would say that the total underwriting risk is controllable, and the same would be true for reserve risk. And in this structure, again, we can change that correlation strength between total underwriting and total reserve risk, and that's going to affect total insurance risk, and really nothing else. So total insurance risk, again, in this method, I would say is also a controllable. Let's have a look at some examples of things that aren't controllable. Let's stay with method 2, but let's have a look at something I might want to change, but it isn't one of these direct nodes in the diagram. So let's say, how would we control class 1's insurance risk? So remember, insurance risk is the sum of underwriting risk and reserve risk. Well, I haven't got an obvious lever. I haven't got an obvious set of parameters that affects just the class 1 insurance risk in this model. I could change class 1's underwriting risk, but I've never had to do that before with these other controllables. I've not had to change the actual underlying distributions before, so that's new. Or I could change the reserve risk, but that's the same problem. I could dial up this correlation between total underwriting risk and total reserve risk, but that's going to have all sorts of knock-on effects, because that's going to change the correlation that all the other classes inherit. So I'm going to end up changing insurance risk for all the classes, not just class 1. And so I would say in this example, class 1's insurance risk is not easily controllable. Let's summarize this just by comparing the two methods and what we've sort of just said. Method 1 at the top, we're calling this insurance risk approach, and method 2 at the bottom, we're calling this underwriting reserve risk approach. So in both cases, I would say the total insurance risk is a controllable figure, and that's almost always going to be true in your correlation approach. That top node is always controllable, and it's probably the most important metric, so that's good. But the key difference is these two. With the underwriting and reserve approach, this total underwriting risk distribution, total reserve risk distribution, I would say are pretty directly controllable without affecting each other. Whereas with the insurance risk approach, I would say that's not the case. And I think this is the big difference between these two approaches. And for me, this would be enough, all else being equal, to select in favor of the second method. I think the total underwriting risk and total reserve risk figures are, generally speaking, very important metrics. They're kind of often used in external reporting, regulatory reporting, and I would say they warrant enough kind of respect to make them kind of controllables through your correlation structure. In total insurance risk per class, may be very important in some models, but I would say in most cases it's a less commonly reported on figure and probably doesn't need to be so strongly directly controlled. So in normal circumstances, I would probably be advocating for the second of these two methods, really just based on this one consideration. Why do controllables matter? Obviously, no self-respecting actuary is going to sort of fiddle their correlation assumptions just to control the total capital number. So we're not doing that. Why should controllables matter to us? And in a nutshell, if something isn't a controllable, then its value is liable to change unexpectedly if something else in the model changes, even if something relatively unrelated in the model changes. So you should choose a dependency structure that makes the key reporting metrics controllable. And let's move across now to a practical demo showing some of these ideas with the capital package. Let's start with the method 1 approach. We are going to start by just setting up a little bit of configuration to help us with the model, so some statistics that we're going to want to see quite often at the end. We're going to set the sim count for the model and import some of the utilities from the capital package that we're going to be using. And let's start by bringing in some data. So we're going to start by modeling underwriting risk. We bring in some premiums data from a CSV file, some loss ratio parameters from a CSV file, simulating some distributions around those loss ratios using a log normal distribution. We're going to calculate the losses by multiplying the premiums by the loss ratios. We can see here that we've got the underwriting risk losses by class. We've got a dozen or so classes and the 100,000 realizations of each. We're then going to do something similar with reserve risk. So we're going to bring in reserve parameters from CSV and again use the simulate values function, again using log normal to generate our reserve risk losses by class. So we've got, again, a distribution for each of our 12 classes or so. Now we want to start applying the correlations. Now with the method 1, we said we were first going to correlate underwriting risk to reserve risk within each class. So this is the data we're bringing in here. We've got a class level underwriting to reserving correlation data file, and it's got a class dimension. We're going to bring that data in, and then we're going to use apply pairwise correlation function to correlate the underwriting losses to the reserving losses, but this is going to happen pairwise. This is the function for applying correlations, so across matching pairs across these two variables. So it's going to match the classes between underwriting and reserving and just apply a series of pairwise 2x2 correlations using the Gaussian copula. So let's have a look at this, and we're then going to measure the pairwise correlation stats for between underwriting and reserving. So let's have a look at that. So this is the underwriting to reserving correlations by class. So these are what we're achieving. So within each class, we're achieving something like maybe a 40 or a 20 or a 50% correlation between underwriting and reserving just within those classes. Once we'd correlated underwriting and reserving, we then aggregated up into a total insurance risk loss figure by class. So this is what we're going to do here. We're aggregating underwriting and reserving and creating total insurance risk by class, and this will have the correlation between underwriting and reserving already included and baked in, but now we're just adding the distributions together post correlation to get this total insurance risk figure. And these now are the distributions we're going to use in that second tier of correlation in the method 1 approach. So we're going to need some new correlation assumptions. So we're going to bring in from CSV file some class-to-class correlation assumptions, and this is what they look like. So these are the target class-to-class correlation assumptions. Again, we've got a mixture of sort of 40%, 20%, 50% between our various classes. And we're going to apply these to the insurance risk losses. So now we want this correlation to apply across these different elements within a single variable. So we're calling the apply element correlation function, applying it to the insurance losses, again doing a Gaussian copula and using these class correlation assumptions. And then we can measure what we've achieved by measuring the correlation stats between the elements using this function. And we can see that we've achieved correlations between the various classes of around the same amounts. So this is the method 1 approach, first doing underwriting and reserving within each class, aggregating, and then doing class to class at the total insurance risk level. So nice and easy to implement. Let's have a look at some stats now. So total insurance risk loss stats, we can aggregate up across all the classes using the sum and then measure the stats on that. Here's the total insurance loss stats. So we can see we've got a mean of around 1.34 billion. In the tail, the 1 in 100, we've got about 1.75 billion. And we can look at that stress, the tail minus the mean, deviation of around 416 million. Let's have a look at some of the other metrics that might be interesting to us though. So we've applied the correlation between classes attaching to the insurance risk total, but that's going to impart some degree of correlation between the underwriting risk figures across the classes and between the reserve risk figures across the classes. So let's have a look at what the inherited correlation is between classes just for the underwriting risk distributions. So we're going to again measure the element correlation stats. So that's the correlation stats between the different elements within a variable. But the variable this time now is just going to be purely the underwriting risk losses. And you can see we've got back some non-zero, non-trivial correlations here. They're not as high as the kind of 20, 40, 50% we were putting in for the insurance class-to-class correlations. They're a bit lower than that because they've shared the effect with reserve risk, essentially. They're about sort of around 70% the strength here in this example. And I believe we had underwriting and reserving being roughly equal kind of weight. So we had some degree of kind of dilution here, but they're certainly inheriting some non-trivial correlation between the classes. We can have a look at the total underwriting risk, again summing up across the classes, and measure the stats on that. And we can see these deviations mean of around 567 million, going up to about 800 million in the 1 in 100. And we can do the same for reserve risk. So again, reserve risk has inherited a similar sort of strength of correlation between the classes, and we can look at the reserve risk stats going from around 770 odd million up to 1 in 200 of about 990. And so this is a useful metric for us to have a look at this stage, because we'll be coming back to this in some of our scenario tests. We've got a 1 in 100 stress for reserve risk of around 220 million. And another number that's interesting to look at as we go into the next example is what's the degree of correlation that we've achieved between total underwriting and total reserving. So we can look at the correlation stats between a pair of figures. We're going to look at the total underwriting losses and the total reserving losses. So these variables are after we've summed across all the classes. And we can see we're achieving something like a 75% correlation between these two aggregate distributions as a result of the class-to-class assumptions we've made and the assumptions within each class. Let's jump across to method 2. We start with exactly the same setup, simulating losses for underwriting risk and reserve risk in the same way as before. So we'll jump ahead to this step. This is where things start to differ. So essentially removing these steps that were in the previous model. So we're no longer applying underwriting to reserve correlation within each class, and we're no longer aggregating underwriting and reserving at this stage because we don't want to introduce any structural dependencies between underwriting and reserving before we get a chance to apply the correlations we want. So we're going to flip the order because in method 2 we first do the class-to-class stuff within each risk period. The reserving class-to-class and the underwriting class-to-class done separately up front. So let's start with that. So we're going to import the same class-to-class correlation matrix as before, but we observed that the effective level of correlation that we were achieving between the classes for underwriting risk or between the classes for reserve risk was actually a little bit less than the correlations that we input to apply to the insurance risk totals between classes. So just to keep things kind of consistent between the two examples, I'm going to put in correlations here that are of the same kind of strength to what we were achieving in the other approach. So roughly scaling these down by about 70%. So these now become the correlation strengths we're targeting. And we're going to apply these to both the underwriting losses and the reserve losses. So these applying within these variables across all the elements. So using that same class correlation structure matrix under a Gaussian copula. So we do those first level correlations, and then we can aggregate. Once we've correlated the underwriting risk across classes, we can sum up across the classes to get a total underwriting loss figure. And once we've correlated the classes for reserve risk, we can sum up across those classes to get a total reserve losses figure. And now we want to go to the second step for method 2, which is when we put the correlation between total underwriting and total reserving. And we observed in the method 1 outputs that we were achieving roughly a 75% correlation between those two high-level distributions. So again, for consistency, picking an input here that's around the same level, just so the outputs from these two methods start off at a similar kind of place. So we're going to apply the correlation now between this pair of values, between the total underwriting risk losses and the total reserving risk losses, using this input 75%. And then we can look at what we're achieving. We're getting that 75% roughly back. And let's have a look at some of these aggregate distributions now. So now we've correlated underwriting and reserving, we're free to add that up into a total insurance loss figure. And again, sum it up over the classes and measure the stats and have a look at what we're getting. So total insurance risk, really not dissimilar to before. We're getting a mean of around 1.34 billion and going up to a 1 in 100 stress of 1.76 billion. So that's a 1 in 100 stress of around 420 million. So not dissimilar to we were getting with method 1. We can look at some of the inherited correlations the other way. What do the class-to-class correlations look like when we measure them at a total insurance risk level? So this, remember, we're not actually applying correlations that attach to total insurance risk. We're applying them separately on the underwriting and the reserve risk distributions. So this will get inherited, and let's see what we do. So we are measuring the correlation between the elements on the total insurance risk losses, and we can see we get this class-to-class matrix, which is achieving things like the the 30-40 sort of 50% kind of correlations that we were seeing with the method 1. So kind of come back to a not dissimilar level of correlation strength, apparent correlation strength between the classes measured at a total insurance risk level. And let's have a look at this other metric that's going to be interesting to us when we start to go on to some sensitivity testing. So we're looking at the total reserve stats and looking at this 1 in 100 deterioration for the reserve distribution, and you can see we're getting around 224, 225 million, which is again very similar to method 1. So these two methods are starting out producing very similar results on a quantitative basis. So similar total insurance risk, similar degree of kind of apparent correlation when we measure things like for like, and similar reserve risk deterioration. Now that we have both methods parameterized and working in Python and roughly calibrated to give equivalent outputs in terms of some of the high-level metrics we've been looking at, we can start to see how these are going to perform under some scenario tests. So the scenario is we're asked to do a sensitivity test in the model and increase the business plan exposures. So it's a very common kind of use of a capital model, exploring alternative business plans and varying the future exposure assumptions. So here we're going to do a test along those lines, and we're expecting to see a significant increase in insurance risk driven by the underwriting risk. And we're going to test both methods, and we're going to use a range of seeds, and we're going to see how both perform under this test. Before we start, we're just going to have a quick look back at the code just to make it clear exactly what we're changing and what outputs we are looking at. So the test is going to just involve doubling premium. So I'm going to simply double premium here. And now we're going to rerun the whole thing. And we're going to look at two metrics. We're going to look at the 1 in 100 stress for insurance risk and the 1 in 100 stress for reserve risk. And here in this method 1, total insurance risk stats. So here we have our 1 in 100 stress. This is now 650. In the previous run without doubling premium, this was about 420 million. And the reserve risk figure for the same metric, so the 1 in 100 stress, that's deviation from mean, is gone to about 190 million, and previously this was about 220 million. So we've seen a reduction in this figure, and we're going to have a look at how that compares to the other method. Let's jump across to method 2, and we'll do the same change. So we're going to double premium and rerun this model. And we're going to look at the same two metrics. We're going to look at the insurance risk 1 in 100 stress and the reserve risk 1 in 100 stress. So let's have a look. We have the insurance risk 1 in 100 stress gone up to around 650 million. So that's a similar change to under method 1, up from about 420 million. And if we look at the reserve risk stress, the 1 in 200, we've got 220 million, which is pretty much exactly what it was before we doubled premium. So let's put all of these results on one page and just try and make some sense of it. We've got here a table. On the top row, we've got method 1. On the bottom row, we've got method 2. And on the left, we're showing the original baseline run. And on the right, we're showing the scenario where we doubled premium. And the metrics we're showing are total insurance risk stress, so that's 1 in 100 minus the mean, total reserve risk stress, and we're also showing a measure of the average class-to-class correlation for reserving, so just the reserving distribution, but measuring the class-to-class correlations and then just looking at the mean strength across classes there. So not a particularly meaningful measure, but just give us an idea of what's going on here. So we can see that these models were reasonably well calibrated to match in terms of these key metrics. So as we compare method 1 and method 2, under the normal premium assumptions, the insurance risk stress around 420 million is pretty much the same in both models, and the reserve risk stress similarly around 220 million is quite consistent, and we're achieving a similar average class-to-class correlation strength for the reserve risk distributions at around 24%. We can see here that this is, I'm calling this the mean. This is the mean across 10 seed runs of 100,000 sims. So it is still a risk number. It's not representing a mean of a distribution. It's the mean of our seed test runs. And we're showing alongside that the range and standard deviation of the seed test outputs. So how stable is this metric as we perform the model run on different seeds? And we can see that both the method 1 and method 2 models have got reasonable stability, sort of a range around 6 million in that output for the total insurance risk, standard deviation of around 2 million. So not a lot between these models in terms of their stability. The interesting thing as we go across to the scenario where we double premium, let's have a look at the first method. We've gone up to around 650 million. This is very similar to what's happened in the second method for the total insurance risk figure. So both have gone up to about 650 million. And that is an impact of just over 50%. So both models are telling us that would be an impact of just over 50% on total insurance risk. That's a reasonably intuitive number. We started off with underwriting risk and reserve risk being roughly equal weight. Now we've doubled just the underwriting risk. So we've doubled half of the distribution. So we might expect something like a 50% increase in the total. But it's a slightly greater impact than that, slightly more than a 50% impact. And that's because we've gone from being in a situation where two distributions were pretty equal weight to one where now one is more dominant, much more dominant. So we're going to get slightly less diversification benefit between these two risks that were previously kind of balanced and offsetting, and now one is overweight. So the other one has smaller diversifying impact on it. So we're seeing a slightly oversized impact of around 50+% here as we doubled that premium. The key difference that I'm trying to draw out here, though, is this secondary impact, the slightly unexpected impact that we're getting on reserve risk. In the second method, reserve risk really has very little impact at all. We're still getting that 220 million result, even as we double premiums. Really not to be a surprise. We haven't done anything to the reserve risk distributions. We've not changed any of the parameters that affect them. So we're really expecting that reserve risk figure to come out as it was, and it has done. And we're getting a similar class-to-class correlation strength for reserve risk, and that's a desirable outcome. I find the result in method one really counterintuitive. We've doubled future premium volumes. That has absolutely nothing to do with the risk on our earned reserves and the possibility of reserve deteriorations there. Completely unaffected by the real world scenario we're testing. And yet the model is giving us this apparent reduction in reserve risk. And this is definitely a systemic effect. There's quite a small range here in these outputs. That 193 is definitely below 220. Across the seeds. So this is definitely a systemic effect that we're seeing here. And why is it happening? It's perfectly natural that it would happen under method one, because we are applying the class-to-class correlations at a total insurance risk level. So the sum of underwriting risk and reserve risk. But now as we double underwriting risk by doubling the premium, we've essentially made underwriting risk a much larger component of that total insurance risk metric. So when we correlate total insurance risk together across the classes, more of that correlation effect is being inherited by the underwriting risk, and less of it is being inherited by the reserve risk. So when we then look at the reserve risk distribution in isolation, the class-to-class correlation has effectively got a bit weaker. And we can see that here, this average class-to-class correlation measured on the reserve risk distribution has dropped from about 24% down to about 19%. And that's what's explaining this drop in the total reserve risk measure. Conversely, what we would see is that the class-to-class correlation strength being inherited on the underwriting risk side has strengthened beyond what it would have been under normal premium assumptions, and so the underwriting risk distribution is getting an extra boost. It's getting a double increase, both from the exposure measure, but then also from this greater inheritance of the correlation structure. And I find this to be probably the big drawback of the method one approach. I think this is a really unsatisfactory thing to have to explain to somebody, a non-model user, an executive who's interested in the results from this sensitivity test. It is not a conversation I would want to have to try and explain to them why it's perfectly reasonable that reserve risk is reduced because we doubled premiums. Intuitively, it doesn't make sense. It's not a real impact that you would expect to see in the real world. You wouldn't really expect to see it out of the model. And I don't think they're going to have a lot of confidence in either you or the credibility of your model if you're going to spend a lot of time explaining to them why these kind of phenomena are realistic. So I would generally tend to avoid methods that allow important reported numbers to move unexpectedly, especially when you're changing things in other areas of the model that really should have no intuitive impact on this risk area. Thank you for listening. Please leave a comment or get in touch on LinkedIn if you'd like to discuss any of these ideas further.